Okay, well, I promised you all a video over the weekend with some more examples of the chain rule. So here we go. Let's review the chain rule though once again. I'll use a pen rather than my finger. Chain rule says that if y is equal to some function f composed with g, then y prime is equal to the derivative of the outside function composed with the inside multiplied by the derivative of the inside function. So we did some examples in class, and I think the examples I picked were maybe a little more advanced than they really needed to be. So let's start off with an easy one. Let's take the derivative of the function y equals cosine 5x. Now the first thing you need to recognize here is that you do have an inside function 5x, and that function is inside the cosine function. So if we decompose it, it would look like this. So the inside function is 5x and the outside function is cosine x. And then of course we differentiate both of those, and we all know how to do that. And so according to the chain rule, the derivative of cosine 5x, well, it's going to be the derivative of the outside function composed with the inside, which is negative sine 5x, and then we multiply by the derivative of the inside function, which is 5. And of course the best way to write this would be to put the 5 in front, so it's negative 5 sine 5x. As a matter of fact, when you differentiate a trigonometric function, the pattern's always going to be pretty much the same. You first take the derivative of the trig function and compose it with the inside function, and then just multiply by the derivative of the inside function. Let's look at one more example. Well, actually a couple more. Let's try this function, y equals e to the x squared power. Once again, you need to recognize that you have one function inside of another. In this case, we have the function x squared inside of e to the x. So if we decompose it, the inside function is x squared, the outside function is e to the x, and then of course we differentiate both of those, and according to the chain rule, the derivative of this will be the derivative of the outside function composed with the inside multiplied by the derivative of the inside function 2x. So our derivative, of course, is going to look like this. So y prime equals e to the x squared times 2x, where it's better to write the 2x, of course, in front. So 2x e to the x squared power. Now, notice also with natural exponential functions, there's also a very common pattern that's always going to be true and you're going to be using a lot. Anytime you differentiate a natural exponential function, the derivative is going to end up being the exact same function again, multiplied by the derivative of the inside function, or the derivative of the exponent. Let me say that again. When you differentiate a natural exponential function, the derivative is going to be the exact same function again, multiplied by the derivative of the exponent. Okay. So let's do a couple of problems based upon these two. Let's try this one. Let's find the derivative of y equals secant of x squared. So remember the pattern I mentioned earlier. When you differentiate a trig function, you simply take the derivative of the trig function composed with the inside function. Now what's the derivative of secant? Secant tangent. So the derivative is going to be secant tangent composed with the inside function. Notice I have secant x squared tangent x squared because x squared is the inside function. And then we multiply by the derivative of the inside function, which is 2x. And let's try this one also. Y equals e to the x squared plus cosine x power. We could go through the decomposing process here for this, but we don't really need to. This is a natural exponential function, and as I said a moment ago up here with the previous example, when you differentiate a natural exponential function, the derivative is simply going to be the exact same function again multiplied by the derivative of the exponent. So the derivative of this is going to end up being e to the x squared plus cosine x multiplied by 2x minus sine x. And that's exactly what I have here as the answer. Okay. So when you differentiate natural exponential functions, it's the same function again multiplied by the derivative of the exponent. Now I promised you that I would do an example where the chain rule needs to be used more than once. So here's a good example. Let's find the derivative of y equals the fourth root of tangent quantity x cubed plus 1. So as we always do in calculus, we always change our radicals into exponents. And let's try to take the derivative of this without having to decompose it. So notice here we have a function raised to a power. So when we differentiate this, the first thing we're going to apply is that power rule for derivatives. We're going to multiply by the exponent, and then we're going to decrease the exponent by 1. So here's my derivative. I'll explain the various parts of it here in a minute. So here we go. We multiply by the exponent and then decrease the exponent by 1. Now we're supposed to multiply by the derivative of the inside function. But notice, just to take the derivative of the inside function, we're going to have to use the chain rule again. So to take the derivative of this inside function, we first figure out what the derivative of tangent is. And the derivative of tangent, of course, is secant squared. So it's going to be secant squared composed with the inside function, and then we multiply by the derivative of that innermost function, which is 3x squared. Okay? So as I said in class, it takes a little while to get used to this if you haven't used chain rule before, but hopefully with lots of practice you'll be really good at it. So we'll see you Monday, and that's all for now.